Hello, good afternoon. Welcome. Thank you for joining us at the 19th Annual Acquisition Research Symposium, hosted by the Acquisition Research Program at Naval Postgraduate School. Welcome to panel number 25, Digital Engineering Across the Acquisition Lifecycle. Awesome topic and the perfect timing to join. I'll start out with a quick background, and we'll introduce the panel members. With that, I'm Gaurang Dävé. My last name spells as Dave. I'm currently a cyber technology officer for the Marine Corps Systems Command. It is the only acquisition command for the Marine Corps. And I'll be chairing this panel, and I'm joined by the panelists, Camryn Burley, Stevens Institute of Technology, Stephen Waugh, John Hopkins APL, Lorri, Bennett, Applied Research Lab, Penn State. I'll start our conversation today, and then each of the panelists will introduce themselves and give their presentations. So a little bit about myself. I'm in the acquisition community for the last 21 years within the government, 15 years with the United States Navy, and last 6 years with the Marine Corps. I am currently serving as a cyber technology officer. I have served previously as a acquisition program manager for ACAT 3 programs, as well as multiple other duties, such as chief engineer for the United States Marine Corps. And I'm currently also acting as a senior information security officer for the Marine Corps as a service. So today we're going to talk about just a quick opening remarks about digital engineering across the acquisition lifecycle. So digital engineering, as we talk and you learn throughout this session, is a lot of times it's known as multiple ways. Some people call it digital transformation to digital engineering, model-based systems engineering, digital twin. They're all referring back to having some sort of a digital engineering, optimizing. So what does this digital engineering optimize? It optimizes the processes, automating the build and the integration of systems, building and integrating more frequently, and testing earlier, more often, and more thoroughly. So what is digital engineering? Why do we use it, right? So as you know, it updates the traditional systems that's used by engineering practices to take advantage of computational technology, modeling, analytics, and data sciences. And on the U.S. DoD side, as you are familiar with, DoD requires robust engineering practices to develop the weapon systems the nation needs to maintain superiority against threats from adversaries worldwide. And you probably came across in your life as DAU describes or defines digital engineering as an integrated digital approach that uses the authoritative sources of system data and modeling as a continuum across the disciplines to support lifecycle activities from concept through disposal, as we call it, as an acquisition lifecycle. So digital engineering, how it impacts the engineers performing their job functions, the tools required, products delivered, and intersection and sharing the data in either locally or distributed environment. And so why do we need digital engineering? I'll give a couple of examples how we use in my environment. As you learn on the acquisition side and on a cyber engineering perspective, we are using model-based systems engineering to deliver easy decision-making for the programmers of record. We have established the process of conducting a digital engineering, digital modeling for Marine Corps Enterprise Network. We start out as a Marine Corps Enterprise architecture. We would collect the data from architecture perspective, and then we put together that data into a model where we can take it to one level up as a system of system model where we can assess technical assessment for any capability that goes on a Marine Corps network. So you can actually easily bring up and conduct various assessment. That could be a cyber threat assessment to a new capability that is going into the system. So it's really costly to conduct a live, a virtual environment, a live system of system actual testing. So we conduct, we call a combination of virtual and hardware in the loop level testing, because so in the DoD arena, some of the systems are not available to actually model. We have some of the tactical systems that we try to bring hardware in the loop with some of the models. So kind of have a hybrid digital engineering, importance of how we tackle the overall system of system technical rigor into Marine Corps level, arena. So on the acquisition side, we conduct model-based systems engineering, and we are moving towards defining a schema that is led by ASNRDA chief engineer for the Naval Systems Command. So you have a common standards. On the logistics side, we use model-based product support analysis to increase reliability and maintainability. So you can actually create a digital model of a physical system and taking that data in and conducting multiple, analysis work. So it would do a technical, inform the technical decision makers on reliability and maintainability level. So we have a great session today. I just wanted to give you a really quick update as a panel chair. I'm very excited to be here today. I am dialing in from the East Coast, so I really appreciate the virtual environment where I don't need to be present there. So those of you from East Coast, appreciate you joining in, and also West Coast, we appreciate you joining this panel. Like I said, we have three awesome presenters. They are panel members. You're going to hear a lot of great things on the different areas within the digital transformation. So what I ask is that please use the question and answer box at the bottom of your screen to post questions for the panelists, and we'll answer the questions after everyone has presented, and then I'll facilitate this question and answer, and I may chime in for multiple additional question as well. So just a quick wanted to do a quick introduction, and wanted to welcome you all. It is an honor to serve as a panel chair for this session, and I wanted to thank the NPS, NPS Acquisition Research Symposium committee and folks for affording an opportunity for me to be here today. So with that said, I'm going to hand it over to Ms. Camryn Burley from Stevens Institute of Technology, who will give a quick introduction and will present the next topic from that. Over.
All right, let me share my screen. All right. So hi, everyone. My name is Camryn Burley. I graduated in December from Stevens Institute of Technology with my master's in space systems engineering. For my capstone project, I created a systemogram of the Defense Acquisition System, and I'll be walking you through that diagram today. I worked with Philip Anton, John Boardman, and Dinesh Verma to complete my project. So first, we will start with some background about systemograms. So systemic diagrams, or systemograms, convey natural language descriptions of complex systems visually. An entire document's worth of information can be represented on a single page, which can then be consumed more quickly by an audience. Because of this, systemograms are especially useful for audiences to converge on a shared mental model of the system and can elicit insight through conversations about the diagram. Both conversations had when creating that diagram and then also about the correctness of a final draft of the diagram. There are some rules that go into creating systemograms. So first, systemograms tell a story about the system and are presented as a series of scenes, where a small number of arcs and nodes are added at a time. Nodes represent noun phrases and arcs represent verb phrases. The main purpose or takeaway of the system is represented as a sentence along the diagonal of the diagram and is called the mainstay. The last node of the mainstay is the overall goal or objective of the system. Nodes are not to be repeated and arcs are not allowed to cross. And then finally, every node must have an input and an output, except for the first and the last nodes. This systemogram was created to provide a high-level overview of the defense acquisition system. The intended audience is individuals just becoming acquainted with the system. So that might be professors beginning research on defense acquisition, or maybe new members of Congress. The systemogram may also have applications for those familiar with defense acquisition in providing them context, recentering them on the ultimate goal of defense acquisition, and providing a means to have conversations about acquisition innovation. But again, the main audience that we were making this diagram for is people who have very little knowledge of the system. Before beginning the defense acquisition systemogram, we generated a list of actors involved in the system and the functions that they perform. Then we conducted research on these actors, which are departments and organizations within and relating to the DoD. I then created a hierarchy to understand the basic relationships that exist among actors and those functions. We used an iterative process where drafts of the systemogram were presented to a subject matter expert for feedback to improve both the accuracy of the diagram, making sure it actually represents the system, and also the readability. We also subjected the diagram to a verification and validation process to ensure that it met the rules of systemogram creation and that it accurately depicted the defense acquisition system. So with that, I will show you the systemogram. I'm going to build the systemogram for you from its scenes. For most scenes, I've zoomed in on the nodes that are relevant to that specific scene, just to make sure you can see them on your computer screen. And then I'll zoom out and show the whole diagram at the end. So we'll start with the mainstay. This is the mainstay of our systemogram, which is the purpose or the main takeaway of the system. Now I'll zoom in so that we can see this mainstay better. So in this case, the threat picture motivates the development of a series of primary enablers, which includes intelligence, funding, technology, and requirements that enable the acquisition community to work with and oversee industry to design, produce, and sustain systems that yield military capability. In this case, the military capability is the ultimate goal of the system. This system also has a feedback loop where the military capability is used in mission operations, which are then observed by combatant commands and service chiefs, and also the intelligence community to produce the threat picture. In addition to the overall goal of generating a military capability, another objective of the acquisition community is to produce effective, timely, and affordable solutions. These trade-offs are reflected in the diagram through the mission, portfolio, and program trade-offs node. The trade-offs between these three competing goals are informed by the acquisition and requirements communities, and the trade-offs also impact the primary enablers. So next, I'll talk about the primary enablers, starting with requirements. So you'll see the blue nodes that have just been added to the diagram all relate to requirements. So the threat picture motivates US government leadership, including the president and Congress, to lay out the mission and strategy, which guides the requirements community to set requirements. For the primary enabler of funding, the president requests a budget from Congress, who authorizes and appropriates to the financial management community to allocate funding. The mission and strategy and requirements communities also set a budget context for the financial management community. And the last primary enabler I'll touch on is technology. The threat picture informs S&T, which is science and technology, who then informs industry of specific needs. Both S&T and industry advance the state of technology, which can drive the acquisition process. And then this is the full defense acquisition systemogram. The last element that we haven't discussed yet is the acquisition community, which is in that large yellow bubble in the middle of the diagram. We've included select functions within the acquisition community to give an example of what happens there, but this is by no means all of the functions they perform. So the ones we've chosen to highlight include oversight, analysis, and root causes, mission, portfolio, and program management, production, quality, and manufacturing, RDT&E and engineering, and contract administration and purchasing, which solicits, contracts, and pays industry. We also have industrial base and supply chain management, who supports and monitors risk in industry, and logistics and sustainment, who sustains, supports, and maintains the systems developed in defense acquisition. So both industry and part of the acquisition community are responsible for sustainment of these systems. And since this diagram is intended as a high-level overview of the acquisition system and how the acquisition community interacts with other functions and organizations outside of it, we chose to exclude interactions within the acquisition community to focus on this higher level picture. So in discussing, making this diagram, we agreed that the acquisition community could be its own systemogram. To keep the level of detail that we wanted for a high level overview, we decided to get rid of those or exclude those interactions. All right, and I will end on the relevance of the systemogram and kind of how we see it being used. So first, this work helps to fill a gap in the literature regarding a high-level view of the overall defense acquisition system, and especially in the form of a systemogram. The diagram also distinguishes itself from other systemograms that are related to defense acquisition by providing a functional flow of the system instead of the typical process-oriented perspective. As I've touched on before, the systemogram could be useful for individuals both within and outside of the defense acquisition system. Individuals outside of the system can learn more about how it works. And while individuals within the system may already know how it works at this high level, the systemogram can generate shared understanding and provide context about how functions and departments within this large enterprise relate to others within the system. The diagram can also help individuals within the acquisition community, or the acquisition system rather, refocus on the ultimate goal of achieving military capability instead of just the immediate objectives of their function or organization. This systemogram also has applications for acquisition innovation. Changes aren't likely to take place at this high level of the diagram, but it does provide shared understanding of the system, which can serve as the foundation for innovation efforts. It makes sure everyone is on the same page about what the system looks like before we're talking about changes. And even if the diagram doesn't show areas for innovation itself, it can at least spark a discussion about its correctness, which is useful to capture knowledge about the system to then be able to tell others about it. The systemogram could serve as the as-is depiction of the system in a systems engineering effort, and then another systemogram could be created to show that to-be version of the system. Innovation efforts would then focus on how to achieve that to-be version from this as-is systemogram. And lastly, the systemogram can focus changes on the ultimate goal of military capability. All innovation efforts should keep this goal in mind and clarify to stakeholders and employees both the importance of their work in relation to this goal. Thank you.
Let's move on to Steve Waugh.
All right. Let me share my screen with you. I'm going to talk briefly about the digital engineering framework, and this is drawn from a systematic review that I did last year as part of my doctoral work. I am very much a weirdo. I am getting a Doctor of Business Administration, and I work at the Applied Physics Laboratory. And trust me, that took more than a little convincing that, no, really, this matters. So it's been an adventure, but it's turned out to be really important. And let's get into it here. So from a content perspective, really got about 10 slides that I want to show everybody today. And we should be able to get through them fairly expeditiously. Introduce you to the problem statement, then the method for systematic review for those who are unfamiliar, cover the 5 major findings of the review, then the resulting digital engineering framework that we came up with, and then some recommendations, conclusions, and limitations. And that'll be where some heresy resides. So we'll get to that. All right, problem statement. For anyone involved in acquisition, nobody would tell you that it's easy or that it comes off on the first try exactly as we had planned. It's very difficult to execute an acquisition plan. And National Defense Strategy acknowledges that, and getting greater efficiency is a priority. So as a result, the National Defense Business Operation Plan said, okay, we've got to reform the business processes. And concurrently, you have the digital engineering strategy come out, and that acknowledges that DoD is lagging industry on digital transformation. So the DoD strategy came out, and it has caused a great deal of confusion and consternation from the deck plates up. There are a lot of people who look at this and don't really understand what it is, what it does, how it works, how it's better. They just know that they need to have a lot of it. So we have the 5 goals of the strategy as they're laid out, in that we're going to use models to make better decisions. We're going to create an authoritative, enduring source of truth, try to incorporate some technical innovations, try to create infrastructure and environments to allow collaboration. And then, of course, you got to transform the workforce to make that all work. So DAU has put out their definition of what DE is. Oddly enough, Congress passed a different definition of DE into law. So that'll be interesting to see if that ever gets sorted out. The long and short of it is that the strategy does not answer the what or how to implement digitalization. So there's a lot of folks wandering around a little bit confused, and they need a little help. So this might be a way for them to organize their thoughts. And it's coming up with this framework for implementation. So the research question was, what are the best practices for digitalization and Industry 4.0 to inform DoD acquisition protocols? Because obviously the commercial world has been pretty deeply immersed in the world of digital for quite a while, and they've had some serious forcing functions. So trying to execute a pretty standard systematic review, first thing is that you frame the question, then you go find the literature, then you break it apart, encode it, and then try to pull out some evidence from across those reviews as opposed to just from a single review. So in this case, the theoretical lens that we applied was general systems theory, and that's because I'm a systems engineer at the lab. I've been doing systems engineering since '97 or so. So it's the one that's familiar. And then, oh, by the way, very similar type of underpinnings will appear in decision science, business process modeling, as well as the systems engineering. Then the literature search is a discipline search. You go into the database, you have your search query, then you pull up hundreds of papers, try to apply some inclusion and exclusion, do a relevance screening, and then finally a quality appraisal. And in this case, I used 2 tools. And the net result was I ended up with 20 papers to go through. Then you start coding the data. And you go through each paper and try to figure out, okay, what is this telling me? And then organize it, categorize it, develop some themes, and then come up with findings. And the net of this is 5 major findings, and will come out in the strategy, process, the output, what the forcing functions are, and then a feedback loop. So let's look at findings. Here's the first one. This is strategy. So here's the input to our overall process. There are 5 major things that you need to make strategic decisions about before you launch on a digital engineering odyssey. And its degree of change, what's the target of impact, what's the circular economy game plan, what are the design principles you want to apply, and then what is the limit of advance for the work. So degree of change. Are we swinging for the bleachers, or are we just trying to get a base hit? How far do we want to go? Target of impact. Are we trying to affect a process, a product, or a service? Because the tools and the technologies that we apply are going to be different depending upon those. Circular economy. How far do we want to transform the data? How much resource do we want to optimize? The data flow processes, how far are we going to change those? How much do we want to shoot for reuse? And then when we look at the Industry 4.0 design principles, and there's a bunch of them, which ones do we want to optimize? Which ones are probably going to have the most impact on where we're going? And then the last piece here, avoiding over digitalization, is critically important. Do not try to boil the ocean. This is a common mistake. It's easy to fall into and will cause the implementation to fail. So there are tools that you can use for each one of those. Second finding is on process. It's like, how are we actually going to do this work? There's a lot of watchwords to go through, but long and short of it is that you've got to have a plan. The evidence indicated design science research would work well. I think any type of project planning approach will work well for you. It's like anything else, you just got to have a plan. So if you got a plan, you're in pretty good shape. But then as you're going in, you need to evaluate the individual opportunities one by one and avoid a set of common traps. So evaluating the opportunities means, for example, if we're going to try to digitalize processes, you assess each process as it is, model it to be, and then evaluate the risk of change. So the traps that are very common are not understanding the customer value, not understanding the value delivery, not understanding the profit. And once you get those into your head, and I'll show you a little bit more later on, it's very easy to do a much better job. So on the output, the back end, what do we get out of this deal? You get a completely new business model. And by that, it means new sets of processes that have been digitalized and new sets of data that will go along and support it. There are some challenges in this, in that the more your processes change, the more they can be changed, and the more you want to change them. So it has a tendency to snowball, and that can be good and bad. You can get carried away with it. There also is some important tension to note between the way that private industry can do this, the way public can do this, but most importantly, in the private-public interactions can be really challenging. Trying to share data between contractors and the government can be a tricky thing. All right. External forces, looking at the world of things that can affect your whole digital effort, this digital initiative that you're trying to launch into. There's a set of ecosystem factors and some technical factors. The ecosystem are things like the people. Who do you have to do this? The resources, how much money or how much time have you got? The organization. Are you a small organization or are you part of a large organization? How much control over your destiny do you really have? What about your supply chain? Who are the people that give you things and people that you give things to? And how are you going to interact with all of them? Then the technical part of that is what are the platforms? What are the computing platforms you're using? What are the ones that are available to you? Welcome to NMCI. That's a pretty serious limiting factor. What about the technology options? Hey, we can go mobile. We can introduce AI. We could do VR. We could do a million different things. But just because you can do them doesn't mean you should. And then data. What data do you have and what data do you need in order to do the thing that you want to do? And starting out, you have to understand which ones are changeable and which ones are constraints. All right, last, feedback. There's two kinds of feedback you're going to get out of this. The first set of feedback you're going to get are internally from users. So you need to have a digital community infrastructure in and amongst your team so that they can tell you what they need and then how it's going. And they're going to, if you keep them motivated, they're going to give you a lot of feedback really rapidly, and you have the best opportunity to put out the best product, as long as there's a free flow of information. But then you need to extend that out to the digital supply chain. Again, all the people who feed you things and the people you feed things to, they're participants in this. And then as time goes by, that feedback loop is going to become more and more robust and will be more and more helpful. The other key aspect is prepare for organizational change. When you're changing your business model, your organization must change with it. If it doesn't, it will fail. All right, next. This is the framework, and we put it together into a single picture. So you start out with the the 5 strategic decisions up front: degree of change, lean impact target, circular economy, industry 4.0 design principles, and delimited processes. That's your strategy. And across the top, we have the ecosystem of things that, generally speaking, inside of the Navy and inside of acquisition, we're probably not going to have a lot of control over. Those are probably going to be constraints. And then on the bottom, we have the technology factors that may or may not be options for platform, the individual technologies, and then the data. And then there's a process by which we are going to evaluate every opportunity that's coming through and avoid our traps in order to arrive at this new business model of digitalized processes and vital data. So the goals will feed the strategy, the ecosystem constrains the technology, process defines execution, and then the new business model delivers the efficiency that you're looking for. Feedback will inform recursion. All right. Recommendations. So what do we do? Well, number one, establish an implementation framework. There are a number of them. This is one, but sit down and say, we're going to do this very deliberately. Then make those strategic decisions, the 5 that we talked about, to limit the changeable processes. Don't boil the ocean. Model the processes as is to be and assess the risk. Engineer the new data model. Right? So down in the data, we're looking at the data that we have and the data that we need. Communicate within the affected users, customers, and suppliers continuously. Keep that feedback, get it going, and keep it going. And then monitor changes to the business model, because you will adjust as time goes down. Now, there are limitations to this. It's a systematic review. So digital engineering, when you go in and you look into all of the databases, Scopus, ProQuest, whatever database you want to go in and look for scholarly journal articles, digital engineering is not a defined branch of engineering, so there are not very many journal articles in it. So it's very difficult to come up with stuff that is digital engineering specific. We have to look for things that are digital transformation, digital modernization, digitalization, and so on, and then see whether or not the information that's resonant inside of that is transferable to these kinds of lessons. It's difficult. The other part is digitalization is very rapid pace. When you go in and look at, for example, inside of the Scopus database and see how many papers have been published on digital transformation, 70% of the articles ever written have been written in the last 3 years. So this is just going off exponentially. The information is changing very, very rapidly. I mean, the technologies available is changing very, very rapidly. So keep that in mind as you're designing this process. The world is going to change under your feet while you're executing. But at the end of the day, if you want to succeed, understand the value the processes create, why we're doing the work, the value of the process, and then the value realization, and you're in good shape. So last slide. Your effective digital engineering framework. If you do it right and pull it all together, you're going to end up with a new business model of new digitalized processes and a new data model that's going to serve whatever program you're working on or functional area you're in or portfolio you're managing. You'll know why you do work, how you do the work, and what you get out of it. That will allow you to make better decisions. All right. The paper is posted online, and actually the presentation that is posted as well has got another dozen slides in backup that are available, and I'll be ready to answer questions as soon as we're done. Thank you.
Hey, Steve, thank you so much. Good, appreciate your presentation. And now, before we move on to Miss Lorri Bennett, I wanted to let folks know we are doing pretty good with the time. So Lorri, if you want to take your time, that's good. And we can come back to Q&A afterwards. But take it away, Lorri.
Hold on a second. Okay, I'm assuming everybody can see my screen. I know somebody will let me know if they can't. Let me put this on. Hold on a second. Okay, so I'm going to assume everybody can see my screen, and I'm assuming somebody will tell me if you cannot. Is it in PowerPoint? Oh, there we go. Okay. Okay, so my name is Lorri Bennett. I work at the Applied Research Lab at Penn State University. I am an R&D engineer and also a department manager. My focus at ARL I've been at ARL for 25 years. Before coming to ARL, I worked in the software industry. My focus at ARL has been on systems engineering research and specifically developing advanced methods and tools and software applications and toolkits or tool sets for engineering, systems engineering requirements all the way down to detailed design. Today, we're going to be talking about capturing engineering process metrics, the idea that we have to start capturing our current engineering metrics on how we're performing in order to improve our acquisition processes. I'll be harping on that a lot today. But I also wanted to mention that my co-contributors that are not here today, maybe they're in the audience, I'm not sure, but Dr. Jay Martin, Dr. Simon Miller, and Dr. Michael Yukish, they are all also research engineers at the Applied Research Lab, but in addition, they are faculty members at Penn State. So Dr. Martin is a faculty member in in industrial engineering. Dr. Miller is faculty in architectural engineering, and Dr. Yukish is a faculty member in aerospace. And all of them have contributed to this work. So as we all know, there's a significant push to accelerate the time to get assets to our warfighters. So we are trying to significantly reduce the time to go from requirements to operational capability. In order to do that, we need to really study the current acquisition process, our current metrics on how we're performing, collect data and analyze that data to figure out how we can improve. But that data doesn't exist. And that is the problem statement that I've mentioned here. There is a deficit of data on this detailed execution of the design acquisition process. These processes need to be measured in order to improve them. In the same time, as Dr. Waugh was mentioning, there's huge digital engineering initiatives going on. And so I'm glad that he brought up some of the 5 tenets from OSD's strategy. There's a big push for engineering to go in using more digital engineering systems, using advanced AI and ML and advanced methods, but also have enduring sources of truth. So instead of disparate databases, have connected databases and have authoritative data sources. These initiatives in digital engineering make it the perfect opportunity for us to start capturing the metrics on how we're performing in the acquisition community. So there'll be roadblocks, and we know that there will be roadblocks because we have a couple of programs where we've already started doing this or trying to do this, capturing data metrics. One of the biggest roadblocks is industry is typically involved in all of our large, detailed design and build acquisition programs. And industry data is proprietary. So that is going to be a roadblock. I can see that being difficult to get industry to buy into some of these methods right away. One of the other roadblocks is that based on our experience trying to collect this data, it's difficult. Some of these systems, specifically in manufacturing, are very large, complicated databases. And it has been difficult to not just collecting the data isn't the hard part, it's correlating the data and associating the data, mining the data in a form that we can analyze it and produce algorithms from it. The other thing is that we're seeing that there's a lack of emphasis on this from the funding community. So we've been presenting this work and talking about this need for a couple years now, but we're not seeing a big emphasis from the funding sponsors on funding more process development. And so I'm going to talk about that today. So what I'm going to do is just really quickly mention 2 programs here at ARL where we started capturing data metrics, analyzing data on how we were performing and how we would collect data from our digital engineering systems. And then I'm going to talk about our recommendations going forward. But before I start that, I wanted to talk a little bit about ARL, and this becomes important. ARL, just as John Hopkins is, we are a university affiliated research center. So we work in the best interest of the government, of the DoD. ARL is a Navy appointed and affiliated research center. So all UARCs are nonprofit and we operate free from conflict of interest. So what I believe is that UARCs and FFRDCs and the Navy lab or the DoD labs, I do a lot of work with the Navy, are the best places to start doing this process metric capture and developing these processes and implementing them. And we can develop these processes in a way that then maybe industry would accept them and use them as long as their data can stay proprietary. So I wanted to mention that as a UARC, we believe these UARCs are a great place to start this type of process. We at ARL have hundreds of engineering, design, and development programs. They vary in level of detail and complexity. We have small UAS drones to large underwater weapons and barges. We go from requirements all the way down to design, build, and test. In addition, we have a large set of digital engineering tools. So we have everything that you would see in industry. We have requirements databases, model-based systems engineering, CAD tools, PLM systems, product lifecycle management systems, manufacturing systems. So we're a perfect place to develop these processes and test them before we move or transition them to industry. So this status as a UARC provides a good opportunity for this work. So the first thing I'm going to do is talk about one of our projects, the first project where we started to capture our engineering metrics. So this was a project, it was a 3-year project that we embarked on with the Rapid Response Technology Office, RRTO. The goal of the whole project was to accelerate the time from requirement to operational capability. So this project was called Operational Responsiveness. We chose to implement this on UASs, so unmanned aerial systems. We also chose to use additive manufacturing as our manufacturing processes. And the picture on the right is a high-level picture of how we were trying to automate this process and significantly reduce the time to in-field operations. So on the left, far left of this figure, we wanted to go from mission capability to in-field capability in days. So it's like a 10x reduction in the acquisition process for a UAS. And so we were doing this all through digital systems. At the same time, we decided to capture all of our engineering metrics, which is relevant to this discussion. So we had a ton of digital systems. The only way this could work is if we fully embrace digital engineering here. And we track things like engineering hours per skill set. So all of our engineers' hours were tracked and what they were working on was tracked. We considered all of our design and test milestones. So as we went from requirements to flight, all of our milestones through the normal systems engineering process, all of our cost, all of our build and material cost, and what I'm going to call our digital footprint history. And that was more of a challenging thing to capture. All of these digital systems were capturing data at a significant rate. We were capturing how that digital data was growing over time and its content over time. That was the intent of this, this program. And so the next slide is going to kind of talk about our results. So what you see here in the graphs are actual data metrics. All of these data metrics we provided publicly. At the bottom, I think the presentation is available to everybody. You can actually click on the link to get all of the data. We published it for other people to do data mining. And what you see here is three of our charts that we produced. One is by project month, the megabytes of data that were stored in our digital engineering tools, the engineering hours that occurred over the lifetime of the project, and they're broken down by total project hours, engineering hours, and UAV hours, so the UAV product. And then on the far right, engineering hours total, and then total hours in the middle, the project and tasking hours accumulated over the time frame. And so our results from this work, we were able to identify trends in the data. For example, what we were able to do is form relationships between our engineering hours, how many hours we were burning, how many hours we were spending per engineering cycle. Oh, and we also instrumented this on 2 full design build cycles. So we did this through 2 full acquisition cycles: requirements, design, build, fly, test, design, and then back to requirements, design, build, test. So we did it on 2 cycles. And we were able to see relationships between the data, but that really wasn't the focus of this talk. The focus was all of what we learned on data collection. So the insight we gained into how hard it was to capture the data. And one of the big things was correlation. So although we had all of these different databases, we had to correlate the data to something common. And what we chose to correlate it to was our milestones. So across the database, we put a snapshot in the time span of when our milestones were for SRR, PDR, CDR, our flight readiness reviews, and all of our tests. And we took all of that data and correlated it to those milestones so that we could create relationships. So that was one of the things we learned from this process. The other thing that we learned is that there is a very human element to this engineering metric capture. We actually had our engineers do self-reporting and capture data on what they were working on and what they could get accomplished. So more of a manual self-reporting as well as the digital systems capture and data capture. That was challenging. We did have to have directives from management to say how important this initiative was, to make sure that all of the engineering staff in the project was willing to report the data that we were requesting. So that was a big lessons learned on this project. But again, it was our first time that we tried to do this metric capture. Another one of our projects, I'm only going to talk about two today, was a much different system. We were working with the major shipbuilder, and we were working on their production bill of materials database, which was a huge database that captured the hierarchical data, manufacturing data as it related to the ship. We were asked to come in through IMAST, which is the Institute for Manufacturing and Sustainment Technologies, and help them automate and create algorithms to automatically detect anomalies and errors in the data. If they could automatically detect errors in the data, it would help reduce manufacturing problems downstream. So we were tasked to create a web-based AI software application to identify these errors. But that's not, again, the focus of this talk. The focus of this talk is the process to collect the data, to mine the data, to correlate the data, and to categorize the data. Tons of lessons learned there as well. The data mining and mapping efforts were challenging. The data for this problem was represented across many different databases. All of the databases had connections, but some of those connections were not useful at all and just muddied the waters, I guess I would say, where other data connections were very important, that actually showed us information we needed on identifying errors. So we learned a lot on data collection and mining from this project. Here's an example of the results. The picture on the left is one of the original data connection maps we created from the raw data, very chaotic and messy, and we could not pull much information from the data. Once we realized that we had this problem with data connections, we implemented these advanced mapping algorithms that identified the relevant connections and the non-relevant connections. And then we could produce maps that had more significant data and information from the PBOM system. Overall, we did a great job of implementing algorithms. We were able to detect 90% of their errors using AI and ML to help them reduce downstream manufacturing problems. Great project. But what we're talking about today is we gained a ton of insight into this data collection, engineering metric collection, engineering metrics collection, data collection. And I also want to point out that we're talking about design and build. So your manufacturing systems as well as your engineering digital systems both have a ton of rich data that we need to really capture and mine on and learn how to improve the process. So in summary, you can't improve our current processes if you don't start measuring how we're doing. I believe that digital engineering and all of the initiatives we have out there currently are going to make this much easier for us. I do a lot of work in digital engineering, and almost all of the engineers I speak with say, I'm already doing it. And they are. Most engineers don't really use pen and paper anymore. They all have digital engineering tool sets in their disciplines. But now we're on the verge of a lot of these digital engineering databases and tools being connected through the digital engineering initiatives, which is going to make our job much easier to collect engineering metrics and get data out of it. So we believe there are we need new research projects that are going to support this data collection instrumentation. So instrumenting the acquisition process. We need to start doing this automated data collection across very complicated data repositories. We have the right skills and capabilities now. Data analysis has to be done to identify the relationships and patterns. This will help us identify where we can improve the process. And then we believe these efforts are best started in the UARCs and in the FFRDCs and in the nonprofits. We can build up good processes and algorithms to best collect the data and then transition those to industry. And with help from the DoD, we can really incent industry to start collecting this type of data, finding areas for improvement and acquisition, and then in implementing improvement opportunity and implementing in those opportunity areas. And I think that's all I had, and I'm looking forward to any questions on this.
All right, Lorri, what a nice presentation by all three of you. Let me start some conversation. I think we have some time I think about 15 minutes or so. And don't want everybody to drag in, but I think it's a great conversation in terms of digital transformation is not an easy thing. If it was easy, to solve it, it would have been done long time ago. And we are still trying to address that, within the DoD. It's more complex in DoD, as most of you, if you're tracking. I was just reading about a month ago or so on Time magazine that BMW was using digital modeling for their components. So industries, have resolved, how to go after, digital transformation, digital engineering to improve, their own parts and systems. And it has worked out pretty good. But what I'm seeing in the DoD, I didn't get to talk more on my background, but I grew up as a software engineer. I came into R&D at Warfare Center in the Navy, and have a software engineering degree, master's in systems engineering, graduate degree in cyber engineering, and it's no brainer as a software engineer. Before even a digital transformation came along, if I had to do same thing twice, I want to write a script that automates that because that's what we do, and that's how we can do things, faster and better and cheaper. So let me go over. Let me start with Camryn. If you don't mind, let's go back to your presentation. Systemagram, talking about systematic diagrams, describing a system view of the key elements. Those of you are new to DoD's acquisition process. It's really, really hard for us, for folks that coming in as a new to DoD and try to understand the process. And it's just sometimes you almost need a PhD to understand how this DoD acquisition process works. So I like the starting as how do you describe a system view of key components, and overall of acquisition system for someone who is new can come in and looking at it at the high level. Obviously, there's a lot goes on when you dissect, things like if each milestone decision that you go through in the acquisition, a process, there's another diagram plays a role. How do you define that? So, Camryn, have you thought about, there's an updated DoD instruction 5000.02, which kind of talks about different, pathways. It's, I think they call it Adaptive Acquisition Framework, or AAF. That, highlights, depends on if it's a major defense acquisition program that you are buying a huge weapon system or acquiring a huge weapon system, you go through certain routes. But if you're using let's say a software enabled system, you can use a software pathways. So I think my question is how do you map that, those different framework, if you thought about it? Camryn, over to you.
Yeah, sure. So, well, first off, I was new to defense acquisition starting this diagram. So it was a learning process for me also, and kind of helpful to see a tool come out of it that I could have used when I started it. But yeah, so we tried to keep it somewhat generic to what the main actors would be in any acquisition program, so that it was the most applicable, and that's what you're picking up first to see. And so we didn't really go into detail about the different frameworks, but I definitely think that they would map to this systemagram, and also a future effort could kind of make a systemagram for each framework and kind of figure out what is different about them and put the different key actors in there.
Yeah, no, totally. And I guess so. You are the like a guinea pig to to see like how when you get into this huge, DoD instruction on how to do acquisition,
Mhm.
and every acquisition is different because when you are, like I said, weapon system, you follow something else. And
Right.
now, if you're looking at a business system, defense business system, or we call it DBS, that goes through different, or different processes, and there's different key holders are involved. So do you have anything in there that, let's pick an example of defense business systems. It goes through different, gate reviews as, like CIO shop is involved and different, you had to certify the funds. Have you thought about some of those actors, like how they would influence, your diagram? Over.
Yeah, so I looked at all of those diagrams to see, what the work products were that come out of different reviews and different stages in the process. And I included them in previous drafts of the diagram, but at some point we've kind of felt that they were too much detail for what we were trying to go for. So they got cut from this draft of the diagram to provide a high level overview. We didn't want to get too deep in the weeds of exactly what report you're generating at that time. But we've talked about, extending this project as you could do systemograms forever on the defense acquisition system at different levels of detail. And so if you did a more detailed systemogram, that could include those work products and the different reviews that happen there.
Okay, makes sense. I was going to ask you for the future follow-on, but you kind of answer that. So I think what I'm going to do also to get to each panelist and ask a couple of things, and then we can, come back and probably summarize this. So over to you, Steve. Right? I was so glad to see when you highlighted that, national defense, the digital transformation strategy, the 2018 that was published, and then the follow-on was in 2020 with the DSET, working group. I'm not sure how much you were tracking because I was part of the DSET working group from the Department of Navy perspective, and some of the challenges we had was how do you actually define or standardize the processes and tools when you have a multiple, system of systems, like let's say example in the Navy, Department of Navy, we have 6 systems commands. They are, meant to do different things. And when you have to, standardize some, processes and tools to make sure that, we all can talk each other and take advantage of their systems that has been already modeled on a digital, environment and reduce the duplication of that system itself. So have you looked, I know during your framework, what is your thought on defining, standardizing process and tools or anything else that is really beneficial for large entity like DoD, when you don't have just Department of Navy with Marine Corps and Navy, but now you're talking with Army and Air Force, and you are in a joint all domain environment. How do you, in your perspective, what would you do? Over.
So the most important thing you can do is change the approach. The problem that we experience now is most of the time, because it's just the easy thing to do, is we find a new technology and say, I have a new hammer. What can I hammer with this thing? Instead of asking ourselves, what's the problem that needs to get solved? And then what's the best way to solve the problem? So standardizing the tool set won't really buy you anything. The real answer is from a ground level up, say, what are the problems that I'm trying to solve? And then standardize processes, and then get the appropriate tools to digitalize or implement those changes. And that will be much more fruitful. Making everyone use Cameo is not the best way to do it. if you're in a small ecosystem inside of a single organization, and you say, look, we've only got we've only got 20 people who know MBSE. Okay. That might make sense to say we've got to standardize something here. But if you're in a large organization, you really need to go grab the tool that's going to be the most appropriate, as opposed to just saying, okay, from now on, everyone uses metric. Well, what about these airplanes over here that still have English standard nuts and bolts on them? So I think that's an important detail that gets lost. The other part is we should not look at, and I think this is very common, particularly inside of the digital engineering community, is that it often is conflated with model-based systems engineering. And if digital engineering is just MBSE plus, then it's just MBSE. If you want to do something different, then it needs to be something different. You got to kind of figure out what that is. So the game for me is to say, let's take a step back. What's the problem we're going to solve? What are the processes? What's the data? And then what's the best tool for the approach?
Yeah, well said, Steve, absolutely. You can't just, ask people to use one tool and then that tool goes away. And then now you're kind of, kept in the limbo as how do you reuse that work? So, good thought there. So I'm monitoring the time. I think we have about solid 10 minutes. I want to take some time with Lorri, and then I want to take about 3 or 4 minutes to summarize the session and then, close it out, if that makes sense. And I'm keep monitoring questions from the participants. If anything pops up, we can address that as well. So over to you, Lorri. Again, another great presentation. And you hit actually, it came to my heart, in a way, because I think you hit some of the points that you described about the understanding the current acquisition process, where you don't have the data that it doesn't exist, and it becomes a big challenge on how do you capture the data, right? So I think what you highlighted, which is my biggest, challenge, is you gotta start with a data strategy, and that is what we are actually in the Marine Corps side. We are helping out. We have enterprise level, high level data strategy, at the service level, but we're trying to address acquisition data strategy, where we can identify how people can capture the data in any sense that is digitally possible, and we can do how data cataloging, and then one of the examples you gave, like using AI related tools, with ML or any other languages you want to do the natural language processing, structure, unstructured data, things like that. How do you, if you have a PDF level documents, with the acquisition community, how do you capture the data? Have you come across any other, natural language reading scripts and tools where you can actually, sweep through multiple, data sets that is not in a structured format?
Yeah, so PDF has become a problem. So we definitely we try to focus on the rich digital engineering tools that exist, because they do provide better data. So what we're proposing is that as everybody moves to the richer systems, like I'm going to have a requirements management system, and I can mine the data directly from those systems instead of the report that's generated from that system. We're really trying to focus on that. But from a PDF standpoint, what we can do is we can try to do a lot of the text recognition and some of the semantics recognition that you see on the PDF. It is still a process, but we're also just capturing the PDF size, right? Like one of the things that we learned is the amount of data stored in a CAD system tells you a lot. So the megabytes, like the amount of data and how that data grows over time tells you how you're progressing down design maturity. Not a clean path, could be a branched path, but it's telling you data. And we just need to dig in deeper and understand what the data is telling you. I think with PDF, the two different approaches is just keeping track of the amount of digital data that's stored with the PDF, but also translating that PDF into systems that can recognize the text and do more like what Camryn was mentioning, where you're then trying to break down the text into searching for certain terms and searching for certain design and engineering content. We haven't done as much with the PDF type of data formats. We're really trying to wait until people move into the richer formats, because that's what we're seeing everybody's doing.
Yeah, no, and yeah, I mean, it's a tough problem, you know, and I think additionally, I think I'll start with you, Lorri, but you know, if Camryn or Steve has any insight also about the data, you know, aggregation in the DoD, when you are looking at, you know, digital engineering piece, you are collecting data on different systems, you know, differently. So I'll give you example on the Marine Corps side. You know, we have systems that we talked about. You know, I think every service has that. You know, business side of the system, we call it garrison. You know, on an unclassified network. But then you got weapon system data. You know, there are tactical systems. So now you're trying to use a digital transformation in various ways. You know, now you are collecting data coming from different classification level, and now you have it, you know, in the storage of, you know, in a different areas that is stored, and now you're aggregating at a higher level model. You know, so how do you do this gating? You know, I guess security check to make sure that, you know, if you are in a one environment, you know, in a DoD, let's say unclass environment, you don't easily go into the next level accidentally and you create a more mess. Over.
I can actually say we are in the middle of trying to solve that problem on 2 of my programs. So I don't know if we have the answer, but we have been asked to help 2 of our programs find and implement their digital engineering strategy. And I really liked, Stephen, I really liked your presentation, because on both of those programs, we're focusing on, let's define problems that you're trying to solve first. We cannot boil the ocean, as you said. And if we try to boil the ocean, we're going to spend a lot of money and not get as much benefit out of it. So we're really trying to focus on the problems we're trying to solve. But one of our biggest problems we're trying to solve right away is, how do we deal with both classified and unclassified data together if we want one authoritative source of data? So I actually don't have an answer, but I can tell you it's one of the biggest problems I'm struggling with right now. And I'm hoping maybe, Stephen, you have a better answer.
Well, so I would actually double down on what you said. I think it's a giant problem. So for example, I digitalized, you know, I was doing a digital T&E model for Next Gen Jammer, and it was a lot of fun. And I digitalized 5 unclassified old test plans, and they were unclassified FOUO. And at the end of it, I, you know, not only was very impressed with myself, but I had created this database of all the resources of all the places and capabilities to test electronic warfare things in the Navy, in the Air Force, in the Army, and at 5 major contractor sites. So basically, I had mapped all of the electronic warfare T&E capability in the United States, which horrified me. The ability to pull that kind of information together and aggregate it rapidly and cause yourself trouble is crazy. But then being able to move back and forth in and out of environments is really challenging. And I don't know how to solve that problem, but it is, I'll tell you, that is a head hurdle. And it's something that we all got to wrap our heads around. The other thing I would like to add to the data question is, I think a real important action that we DoD can take is to embrace the concept of a chief data officer. A lot of programs with the chief engineer, the chief acquisition person, and the chief whatever, is that if we have a chief data officer whose only responsibility is managing the data, right? I'm going to make sure the data that comes in is quality, the data that goes out is quality, you know, it's all kept in one place, but then, you know, It is for a purpose. And I'm not making decisions with it. My job is to take care of it. I'm like the plumber for data. If we do that in programs, you have oceans of data, particularly in the logistics world. Just untold volumes of information that simply will lie there and are unused. And if we can pull that together, then I think that will make an enormous opportunity for all kinds of data mining.
All right, so it's I see it on my East Coast time. It's 6:06, and I was told that we were all told that it will disconnect in 4 minutes, regardless where we are. So I want to take the time right now and first thank you, all of you. Starting with the panel members. Camryn, Steve, and Lorri. I really appreciate putting the time and presenting today, and the NPS folks for. Hosting this symposium and participants for joining us. So, I'm wrapping up this session, and I think we all know that this digital transformation is it's not an overnight thing that we can change, and we also know that as evidenced across the services and industries, that digital engineering is a necessary practice to support acquisition in an environment of increasing global challenges and dynamic threat environments. We gotta leverage this. We have started this. We need to solve this as working together as, leveraging academia, industry, and government partnership. This is not a one entity solving, this problem. And in my opinion, this requires a culture change. And especially on some of the DoD entities, we have to show to the workforce that some workforce may need training and adoption. That people are not used to doing this. We also see it in the program managers. Sometimes they see they don't see return on investment immediately. It takes some time for them to see all that. So. I think it's our as a technical leaders, I feel like it's our job or try to solve this problem and help out in all numerous ways, and starting with actually that DoD. I look at the DoD and helping out contract modifications. That solves what Lorri brought up, that we need digital data from industry. Right on the data that government is paying for it, so but then it also introduces some cost, because industry is going to ask for more money to share that data, right? So I think this can be doable. We have adopted that with a small team, try to help out with the engineering workforce within the government. Anyway, we will solve this. It's great. Exciting topic. I appreciate everybody, and thank you so much for joining.